Today we are going to study the Lennard Jones potential. This is an intermolecular pair potential which models repulsive and attractive interactions. It describes neutral atoms and molecules. Consider two atoms A and B at a certain distance from each other. As shown. This is atom A and this is atom B. This line represents the center of this atom. Moving away from the center, the charge density decreases. At sufficient closed separation, the overlap energy is repulsive due to Pauli exclusion principle. The charges overlap only when the electrons in B jumps to higher level and the electrons from A occupy the state thus the total energy of the system increases. This is the repulsive contribution to the interaction. The empirical potential energy U is of the form UR B divided by R12. This can be calculated using the experiments. Where B is positive. Similarly, the attractive part, which is the contribution from the van der Waals interaction is minus A divided by R6, where A is negative. Let us draw the potential energy versus distance for the above system as shown on horizontal axis. We will plot the potential energy, while on the x-axis we will plot the distance, which is represented by r. At sufficient distance, r, the potential energy is negative, and it is the attractive part of the Lj potential. If we decrease the distance between the atoms, the energy decreases in the negative direction. The potential reaches a negative maximum at U naught. This is U naught. This point is called the equilibrium position. If we further decrease the distance, then the curve will reach a point where the potential is zero. If we further decrease the distance, the potential enters into the positive region of the curve. This is u equal to 0, and this is the repulsive part of the curve. This complete curve is called lennard potential. The equilibrium position occurs at a distance of r naught, while when the potential is 0, the distance between the two atoms is sigma naught. We'll explain these r naught and sigma naught later. Now we will calculate the potential energy between atoms at u naught and at some distance r. The two potential energies can be written as U attractive is minus A divided by R M, while the repulsive is B divided by R M. The total potential is U B divided by Rm minus A divided by Rn. This is equation 1. We need to find A and B in terms of m and n at equilibrium position, the net force is 0 because the repulsive and the attractive potential will balance each other. We can write the force as a minus del u divided by dr when r is equal to r naught, and this will be equal to 0. Now, using equation 1 and applying the condition, we will receive mb divided by rm plus 1 minus na divided by rn plus 1 equal to 0. This is the first derivative with respect to r of the equation 1. mb divided by r m plus 1 is equal to na divided by rn plus 1. Here r will be now replaced by r naught as mentioned in the condition. Na by further simplification, Na divided by mb is equal to r naught n minus m. This is equation 2. At equilibrium position, mu naught r is equal to r naught. The equation 1 can be written as mu naught b divided by r naught m minus a divided by r naught n. Mu naught is equal to minus a divided by r naught n. I am taking minus a divided by r naught n common from the equation. 1 minus b by a, this is r naught n minus n. Now, using equation 2, we can write mu naught as minus a divided by r naught n 1 minus n by m. This is equation 3. Now, at r is equal to sigma naught distance, the potential is 0 using equation 1 b divided by sigma naught divided by m minus a divided by sigma naught to the power n equal to 0. We are replacing r by the sigma. R b divided by sigma naught m is equal to a divided by sigma naught n. This is further equal to b by a is equal to sigma naught m minus n. This is equation 4. Putting the value of b by a in equation 2, we get n by m sigma naught n minus m is equal to r naught n minus m, or r naught equal to n by m 1 over n minus m sigma naught. This is equation 5. Now, Using equation 3, let us find the value of A, which is equal to minus u naught Rn m divided by m minus n. And this is equation 6. Now putting the value of R naught from 5 in equation 6, or A will be equal to minus mu naught n by n divided by n minus m divided by m minus n sigma naught n. This is equation 7. Similarly, for B, using equation 1, u naught is equal to B divided by R naught m minus A divided by R naught n. U naught is equal to B divided by R naught m 1 minus A by B R naught m minus n. This is now using 2. This u naught will be equal to B divided by R naught m 1 minus m by n. That is B divided by R naught m n minus m divided by n. This is equation 8. We have followed the same procedure to calculate B. B is equal to u naught Rm n divided by n minus m we will put the value of R naught from equation 5. Then B will be equal to mu naught n by m divided by n plus m n divided by n minus m sigma naught to the power m. This is equation 9. So equation 9 and 7 gives us the value of A and B using the general equation. The potential is B by Rm minus A divided by Rn. Putting equation 7 and 9 in this general equation, the u will be equal to u naught n by m n minus m sigma naught divided by r plus n by m into m minus n sigma naught by r to the power n. So this is the general equation for the potential. Now using m is equal to 12 and n equal to 6, as we know that this m is equal to 12 is from some computational calculations, and this terms is from the van der Waals interaction. The potential, by putting these values, the potential will turns out as 4 u naught sigma naught by r to the power 12 minus sigma naught divided by r to the power 6. This is the general standard equation of Lj potential. Here r is the distance between two interacting particles. U naught is the depth of the potential. The potential will, sometimes it is called dispersive energy, and sigma naught is the distance where the particles particle energy is, interactive energy is, E is 0, means U is 0. This sometimes it is referred as the size of the particle. The size of